So how do we represent colors and images in binary? Well, every binary bit, a single 0 or 1, can represent either on or off. And these on or off switches, when collected in a group of 8 bits, otherwise known as a byte of information, can represent a total of 256 things, 255 plus 0. The 0 also is 1. So of 255 being the highest number you can create in binary, bi meaning 2 like a bicycle, those two numbers, 0 or 1, and we can create all the way up to 255. So using a byte of information, 8 bits over here, we could represent numbers between 0 and 255, a total of 256 things. So using a system of mapping each one of those 0 through 255 things using RGB, red, green, blue, we can represent individual colors using the idea of something called a pixel. And a pixel is just the smallest elements in an image. And if you zoom all the way into a pixel, you would see the 3 different colors, red, green, and blue. And we're able to create, using these red, green, and blue colors, any single color that you could possibly want to create using the idea of additive colors over here. You might think that normally, like red, green, blue, those are not the primary colors you'd be using in like real painting over here. But that's because using subtractive color is what those colors use over here. We need to be able to add the colors using an additive color palette, where the more color we add to it, the brighter it gets. So we can add colors together and we'd get white, where don't have any of them together, and we'd be able to create black over here. So using the additive color model of RGB, if we set all of our values 0, 0, 0, we would create the color black, or the shade of black, and the closer to 0, 0, 0 we are, the closer to black it is. So if we have a very muted red over here and no other colors, we're going to have something that looks really, really close to black. But if we keep increasing this, it's still going to be a dark red, but it's getting lighter over here. So what does 100? So what is this particular shade? What is it? So this is 100 red, 0 green, and 0 blue. So in total over here, there are 3 different values, all of which map to a string of bytes, a total of 0 to 255. So if we were to have the number 100 for red over here, 100 for red in binary would be represented over here at 64 plus 32 plus 4, or the string 0, 1, 1, 0, 0, 1, 0, 0. So this string of binary would be lighting up on the little transistors inside of a computer. Inside this computer, everything that you see here. And then for the other colors, so that's the first byte, this 8 over here. And then the other colors, the green would be represented right now on these bulbs at the same time at 0, 0, 0, 0, 0, 0, 0, 0. And the blue would be represented at the same. So those 24 strings over here, 0, 0, 0, 0, 0, 0, and then the number 100, which is 0, 1, 1, and then 0, 0, 1, 0, 0, those 24 different transistors are going to light up in that binary string, and using a program that's able to map colors as opposed to like a word processor like Microsoft Word, those 24 transistors would light up and we would get the individual single pixel that we can see over here. This is kind of like this maroon color over here. So this one pixel of maroon would then be represented by those 24 bits. So if we wanted to create an emoji, or look at like an emoji keyboard or something like that. So a single emoji is, generally speaking, on the Apple keyboard, it's 128 by 128, which is simply the number of pixels inside of that emoji. So if we had tears with joy emoji over here, those 128 pixels over here, if we were to zoom into that picture, there's some blue, there's a little bit of white over here. So let's pull up the tears with joy Apple emoji so we can take a closer look at it. So this emoji over here, we can see that there's a little white over here. There's some lighter shades of blue. There's a darker shade of blue on the outside. There's kind of darker yellow all around it. There's, I'd say, a brown and then a lighter brown inside here, a grayish white. So each of these individual colors, so this grayish white, every single pixel, if we zoomed all the way in, that grayish white over here in RGB probably be something along the lines of these 24 string of binary code over here. And then for each of those colors, maybe that muted, the darker yellow would be something like this over here, 208, 198, and 68 additive these colors, overlapping these colors in a color wheel that looks exactly like this. So these overlapping colors, these values, once the closer they get, the closer to white that they're going to get over here. So we can create any color with these red, green, and blue values, and we can map those to a group of binary strings. And for every single pixel, which is made up of those, a little bit of red, a little bit of green, a little bit of blue, those colors add together to create whatever color that you're trying to create. And that emoji has a lot of different pixels, and each of those pixels specifically, well, how many of them? Well, if it's 128 times 128, that means that there are 16,384 pixels. So each of these pixels is being represented by 24 strings of binary code. So that emoji is, multiply that by 24, that there are a total of 393,216 different transistors that are lighting up, where those little transistors that are lighting up, there's a group of, for each individual pixel, there's 24 of those strings, a little bit of red, a little bit of green, a little bit of blue that light up, and those represents, that is the data that's representing this single emoji over here. Now, let's say instead of emoji, you're trying to represent like a bigger image. Well, if you looked up, for example, let's say you're going to the movies and you wanted a single cutout image of a screen. So if we were looking at like what an 8K image looks like. So an image that's in 8K, this beautiful, whatever, imagine whatever it is, movie or image or resolution. So 8K has a particular screen size. So if we were to look at what's known the aspect ratio, which is how wide and how long the image is, the aspect ratio of what is in 8K over here, the dimensions are, it's usually 16 for the length and 9 for the height. And if we look at the pixels inside of that aspect ratio, we can see that it's going to be 7,680 in terms of the 16 or how long it is, or the 4,320 pixels for how tall it is. So if we had one single image in 8K resolution over here, if we multiply this together, that means that there are a total of 33 million pixels on that one particular image. And every single pixel is represented by a certain amount of red, a certain amount of green, a certain amount of blue. So that's a total of 8, 8, and 8, or 24 different strings of binary. So 24, if we were to multiply that over here, so 24 times that big number means that we have over here 796,262,400 individual little strings of pixels that are represented with that many strings of binary code over here. So that's a lot of code to represent a single image. And to take this one step further, and it's the last thing that we're going to do, that's one image of a movie. Every movie, a video, is a collection of moving images. So I'm sure you've heard the idea of FPS, frames per second. So frame rate, if there are 60 frames in 1 second, then 1 second of a video would be 20 or 60 times that one image. So that one image, which is using this many strings of binary, times 60 images in 1 second, this number is really, really, really big, but this is how many 47 trillion strings of binary code for a 1 second 8K video. Now, 1 second's not very long. Let's say that we had not just 1 second, but 60 seconds. So if we had a 60-second clip, it gets even bigger. And if it was a 60-minute movie, it gets even bigger. And if we were to try and represent what this number is without it having all those decimal places, it's 1.7 to the 14th power, which is a very big number. And it's in scientific notation, and we could remap this out. We don't have to. The point is it's just really, really big, and videos, for that reason, you might ask yourself, why do videos take a long time to load or upload? And the reason is because of the sheer amount of information it is. It has so many pixels, which is so many binary strings, that it's just going to take a really long time to upload. So that is why video streaming takes a while. It's just a lot of information, and it's a truly magical, miraculous thing that we have all of this information at our fingertips that we're able to do. So yeah, so that is RGB. These are binary bulbs. I encourage you guys to play with the binary bulbs, play with RGB, try and create a color, and think how much red, how much green, how much blue it is. Closer to 255, it's additive, so the closer to white it is, closer to 0, the closer to dark it is, and anywhere in between. So I hope you guys enjoyed. I'll see you guys in the next video.